Good day, folks. This is tutorial number 34, which is actually a follow-up to tutorial 33, dealing with the rolling disc supported by two springs. Uh, I did this problem in tutorial 33, but there are some issues that I did not want to raise, and that's why otherwise the tutorial would get too long, and therefore I decided to do that in this particular session. What I did there was to model this problem, a very elementary problem in a vibrations course. Basically, you have a disk attached to the two springs as shown, and this disk is rolling on the ground without any slipping. The objective is to find the natural frequency of vibration of this disk. In other words, if you give it a slight tilt, as you roll it a little bit, a small angle, and then let it go, obviously this will oscillate back and forth between the vertical position. Now, uh, the problem can be solved analytically, and you can find it in most vibrations textbooks. And the natural frequency is given by what you see there, and the period, of course, is related through that formula. So I modeled this problem, and the way I did it, I actually created this geometry, and what we have here is this point where the connection between the spring and the disc is 30 centimeters away from both sides. And when I define the spring properties, for the spring on the right, I said the natural length is 32. That means that because it's at this location 30 centimeter away, it's already compressed. The spring on the right is already compressed because the reference length is 32. And by the same token, the spring on the left, the reference length being 28 inches, and now it will be positioned so that the distance is 30, means that this is already stretched. Okay, so I did this problem, and gravity, because we're dealing this thing in dynamics, the dynamic scenario creation, you need an excitation, and the excitation is gravity acting down. This gravity does not come into the formula that I showed you, but you need it in order to run a dynamics analysis. Okay, it will actually come into the picture later on, as you'll see. Now, uh, the geometry and dimensions are given here. What I did, I created the roll curve joint, a roll curve joint between the circle on the disk and the horizontal line on the ground, and a planar joint between the vertical face of this disk and the vertical face of this wall. Okay, so and I use the DASSL integrator, which stands for Differential Algebraic Solution Solver. And let's move on for a duration of 0.4 second, almost four vibrations. Now, I want to go back and bring this up. First of all, if we if right now everything is made, and if I look at this mechanism manager, you see that I have two springs, a fixed part, that's the ground, a planar joint that I talked about, and a roll curve joint. And just to show you what happens, reminder, we're going to run this thing. You have already seen that in tutorial 33, and everything will look fine. And I actually went and plotted things and showed you that the frequency of vibration is, or the period of vibration is very close to what we have in mind. Now, what I then said is that, okay, what is the role of that planar joint? Okay, so let's go ahead to this mechanism and check all our joints, double click, and let me go ahead and exclude that planar joint. Planar joint is excluded. So we have a roll curve joint, and of course there are springs, and the gravity is acting down. So let's go ahead and run this thing. So we go here, run it. Notice there is no planar joint. Look what happens. These are still rolling on each other, but uh, because there is nothing to hold this thing vertically up, such as the planar joint, it'll gravity make it go through the base, which is really not what I want. Now, of course, there are ways to fix this. You can put a planar joint back on the back side, or if you insist, you can create you know, a point curve joint between, for example, the center of the disk and a line that's drawn horizontal. It is possible to do that, okay? But I want to show you a different thing, and that is, okay, now let's say that we go and we uh, uh, add, prevent the penetration of this disk through that base. Now, how do we do that? We create a contact between them and let it run. So don't let this disk penetrate through the base. So what we're going to do, we're going to go to um, uh, the place where we can actually make our joints. So let's go ahead to switch to mechanism right there. And now we're going to create a contact. See that? Contact, contact right there. We create a contact. Okay. Now, uh, because this is surface contact and we're going to use DASSL, we just select this second tab, surfacic contact model. And I don't want any friction, so I made the friction equal to 0.0001 as a static, as a coefficient of friction. Now, ideally, I can make this thing zero, but if you make it zero, it's going to come back and say you can't have a zero value here. So I made it very small, all right? And say, we're going to create our contact groups. So click on the plus sign, select the disk. Here it's going to go in there. Say OK. And now select group 2, plus sign. Select the base or the ground. Say OK. So we have contact between disk and the ground with that coefficient of friction. We say OK. Now, if you click on the mechanism manager, because I did this thing now, it is not included. Remember, planar is already excluded. If I add contact here, if I add contact, see this? We say OK, and now we're going to run it. So we now have contact established between the disk and the base, and let's run it. It will not go through that ground. That's good news. Contact will prevent doing that, okay? However, uh, let me do this thing for a longer period. Let's make it. Actually, let me do the following. Uh, let me change the integrator. Let me change the integrator from DASSL to symplectic and say OK and run it now. Okay, it wants this value to be smaller than that. Say fine. Let's go ahead and run it and see what happens. So you can see that contact will actually change this thing back to no problem. Contact will prevent this thing to go through that. But let me go and take that roll curve away. So I go back to my mechanism, go back to mechanism manager, and take away the roll curve option. So we have contact established and but no roll curve. So let's go ahead and run it. Ah, you see, this happens. And the reason this happens is that this spring, when you look at the problem that we are solving analytically, must also be present on the other side. So you see what happens. Good. So let's go ahead and do the following. First of all, I need to create 2 more springs in the back of this and also reduce the stiffness of these springs into half. So let's first do that. I go here to my spring. It's the first spring. Double click on it. And for stiffness, I make 3,000 for each one of them. This is the first one. The other one is over here. Also 3,000. So, okay. All right. Now we go and create two more springs on this side with the same stiffness. Now, I need a point at this on this element at the height of 1.8, just like the other side. So let me go to that part. Okay. I'm in that part right now and create a point on this plane. Yeah, on this plane. Right there. Okay. You say, okay. Took longer than I expected. Okay, now we're going to go to the place where we can create joints, right? So let me go ahead to mechanism right there. Here's another spring, axial spring. So yeah, between this point and where's my other point here? Just 1 second. That was created in the disk, right? It's that one, right? Yes, right there. You can see that. And the stiffness f of x is going to be 3,000. Yep. We do another spring from that end to this point. Another one from, maybe I'll do this one and that one. Get through this. This one, this point, this corner point, and this point too. And the stiffness value is going to be also 3,000. So we have, now we have 4 springs, 2 in the front, 2 in the back. The stiffnesses are reduced by a factor of 2. Oh, I forgot to do the reference length. We have to do that. Let's not forget, because that's critical. Where are these springs that I created? Oh, notice that, by the way, it doesn't show up in my joints here because I just created them, and I'd have to include them if you want to see them right there. The only thing is that I have to fix the values right here for reference length. So this first one was the one on the right side, and the reference length should be 32. Okay. Actually, I'm not sure. I'm not sure now. We'll find out. We'll find out. One of them is 32. The other one is 28. I really lost track of it. But let's see now. Go here. Reference length. I'll make it 28. If it doesn't work, I'll flip. I'll swap them. So I forgot which one was the first one. Okay. So notice what happens here. We don't have any roll curve. We have contact, and we have 4 springs, and the springs are half of what was in the front. So if I run it, it better roll properly. Otherwise, I made a mistake in those reference length. We'll fix it. Yep, good. I think that's okay. You can see that it doesn't twist as it was doing before. So the point is that there are many ways of doing some of these problems, and in tutorial 33, I used roll curve. Then I said, that's really not necessary. You don't have to. I'm sure if you looked at the plot and calculated the period, there's going to be some differences. But let's actually check it out. We go here. Let's go wait for a second and check the period of oscillation. Deselect all. Look at the y displacement, and let's check the period. So remember, start at 0, 0 times 0, and the next time it goes to 0, we check the time. So next time that it goes to 0, y vertex goes to 0. So we go up to 0.123. See, this is the time. This is where it's going to go back essentially to 0, because after that it keeps increasing. See, this is decreasing, 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 decreasing up to this point, and then increase. So it didn't change the period of oscillation. That's good. Good luck.